Welcome back. Lecture 14, Math 141. I received an email late last evening about a question in the, is it 2.5 or 2.6? 2.6 WebAssign. And I want to address it so that it actually makes it to the broadcast and then makes it to the DVDs. The question is number 5, I believe. And some of the question, I think, is really valid because it gets you thinking about the slope of the secant. And as the 2 points get closer and closer together, the secant line gets more and more like a tangent line. So that's valid. So Part A and Part B, I think, are pretty valid pieces to the problem, and you could see them again on a test or quiz. Part C, however, is an estimation. And depending on the tolerance that is set in WebAssign and the method that you happen to use. So Katie uses a method where she gets an equation of best fit, and then she's had some calculus before, so she takes the derivative. You even took the derivative the long way, right?
Yeah, I did it both ways.
Okay. And so she comes up with an answer that is not within the tolerance of WebAssign. In all honesty, these are probably not good WebAssign questions because you're being asked to guess. What's wrong with your guess? Your guess is better than his guess or her guess. So I think Katie's guess is better. So here's the way that the solution manual proposes that you do this problem. It is a way to do the problem. I don't necessarily think it's the best way to do the problem. But if you have done Part A correctly, basically difference of the y's over difference of the x's from 1994 to 1996, difference of the y values over difference of the x's. These are slopes of secants. Same thing here. So these are valid. This is very, in fact, I think pretty darn good problems. You're using probably fairly realistic data and you're coming up with some results. But these are secants. These are average rates of change. Now it says in Part B to use two slopes of secants, average them, and maybe that's a pretty good approximation of what would happen with the slope of the tangent. Okay? That's valid. That's what's done here. You take the two answers from Part 2 and Part 3 and you add them together and average them. So maybe that's a fairly good estimate. This method, here's what we're really looking for, the slope of line segment AB, slope of the tangent. So their proposed method of solution is to construct this right triangle, take the difference of the y values, so I guess the y value up here minus this one, that's where this comes from. Some of those values may not look familiar. They're estimates. Difference of the x values, this x value minus this one, that's down here. And they come up with this answer. It's an estimate. So this is their estimate. That's not to say that your estimate isn't just as valid. So bad problems. You can get 100% at the end of the semester on WebAssign, even though you don't have what looks like 100% of the points achieved. Because I know there are several problems throughout the semester that asks you to do that, to estimate. And you'll never see a test question like that. I can absolutely guarantee you that. It's not necessarily a bad problem, but it's a bad problem for WebAssign. Katie?
When you do the subtraction, like you said, the point C minus point A for the distance of that base or whatever it is, the 10,182, like, I don't understand where you get that from, because it says to use the 1998 10,182 point. Then the problem before that, the point is 1998 10,175. So they have different y values.
That's correct. That is not a point on the curve.
So
they have started with that line segment.
So it's really the point. Okay, never mind.
Yeah, the point you're talking about. Do you see the difference?
Yeah.
The point you're talking about is this point, and then the point that they're using is that point. So
Okay.
they've counted, they've estimated. I don't think their estimation is any more valid than yours.
Okay.
And then same thing with this point. That's by taking that line segment and forming a right triangle. That's how they've come up with those points.
Correct.
So don't worry too much when a problem asks you to estimate. Go ahead and estimate. Make a couple of reasonable stabs at it. Jonathan said he put in 15, right, and it took it. Anybody else get a value that was any further away from this number that homework, it actually took it as correct? So it has some tolerance built in. You don't have to get exactly this answer. But I don't know which is better, if 14.25 thousand per year is better, or I tend to think by the way you did the problem, by getting a curve of best fit and taking the derivative, I would tend to trust that.
I found the curve by hand, and it came out to be pretty
I
close.
would trust that a little more. But don't worry about the points lost, so to speak, on WebAssign. Okay, we kind of in the middle of a problem. Let's see if we can resurrect what we had done. We started with an S of t. I think that was it. Is that correct? That was our distance, height, or position. We decided that what this represented, because the initial position of the object was 1,000 feet, so it starts 1,000 feet off the ground, and then it was just released. Okay, it wasn't projected upward, it wasn't projected downward, it was just released. Now I think we'll be able to validate that release as opposed to projected upward or projected downward. I think right at the end of class we did the velocity by taking the instantaneous rate of change of position with respect to time. So we did the kind of the definition of derivative. I'm not going to go through it all again, but I'll get the start and the finish. So we did the S of t plus h minus the S of t that's an interesting noise. I wonder what that is. All over h as h approaches 0. All right, so we did this work, right? We did the algebra. We knocked out like terms. We divided everything by h. And we got the v of t to be what? Okay, I think that's where we stopped, right? Because in fact, we were rushing to get to that point. Let's see if we can validate the fact that this object was just released from the top of this 1,000-foot building at time 0. So we want the velocity at time 0. So if we plug that into the equation, and use the appropriate units, its initial velocity was 0 feet per second. If it were projected upward, wouldn't it have some positive initial velocity, right? And if it were projected downward, it would have a negative initial velocity. This was just released. So at time 0, its velocity was 0, which means it was released instead of projected upward or downward. If we want to know its velocity at time 1, we have this new function, this velocity function. So the velocity at time 1 is negative 32 feet per second, which means it's on its way down, right? That's the negative sign. And the actual speed of it is 32 feet per second. But it's negative because it's on its way down. Is that what your question was? Okay. And we could continue. Now, realistically, in this problem, if I wanted to see the velocity at time 10, that's absurd in this problem. Why is that absurd in this problem? It's already hit the ground, right? So we can find the velocity all the way to the point in time where it hits the ground. Excuse me. We decided yesterday that it hit the ground at, what was that? 7.9, 7.91, something like that, seconds. Excuse me. So even though that's absurd, it's already been on the ground for, a little more than 2 seconds, we could find the velocity with which it strikes the ground, right? At that very instant, how fast was it going? The instant that it struck the ground. We could put 7.91 in there. Somebody help me with that. What is that? Excuse me.
Negative 253.12.
And that is feet per second. So at the very instant that it is striking the ground, that's how fast it's going. Soon thereafter, it's just sitting there on the ground, right? So we can't do anything with that, but that's the velocity with which it strikes the ground. So we have this equation that we battled a little bit yesterday to get. And we found it by taking the instantaneous rate of change, the slope of the tangent, and we gave that another name called the derivative. So we started with an s function. We found the s prime of t. That's the derivative of the s function. That happens to be the v function. What happened in this first second that transpired? Initially, its velocity was 0. During that first second, it lost velocity, or if you want to think of it as a gain, kind of a net gain, to 32 feet per second. So during that first second, we had a change in velocity of 32 feet per second. So I'm trying to get to the point where I'm almost saying 32 feet per second per second. What's that sound like?
Acceleration.
That's acceleration. So if we were to take this equation, we kind of see that illustrated right here. If we were to take this velocity equation, I'm going to move this sheet. Any questions about what's here before it gets moved? So we started with this. We took the derivative. We called it the velocity. Hopefully it sounds like velocity. Instantaneous rate of change of distance with respect to time. Sounds like a velocity to me. Now, if we start with that, excuse me. The instantaneous rate of change of velocity with respect to time, first derivative of velocity, ought to be acceleration. So our v prime, sorry that's a little crowded there. The v of t plus h, this is a whole lot easier than the s of t plus h. Minus v of t while we're writing this down, we can think of the fact that today is Mandy's birthday, and we're all thinking about wishing Mandy a happy birthday today. Happy birthday, Mandy. Got to get that on tape. We'll just leave it at that, because somebody might actually hear my voice during the dinner hour, and that would not be pleasant. All right, what do we lose in the numerator? Minus 32t plus 32t. Everything in the numerator has an h. Factor that out. Not a whole lot left after that. And as long as h is not 0, there's no h in there anymore. the limit of negative 32. H can be doing whatever it wants to do, as long as it's not 0. So we get a constant for v prime, and we decided up here that v prime is actually acceleration. So we are starting with a distance, height, or position function. Take its derivative, we get velocity. Take the derivative of velocity, we get acceleration.
Is that feet per second per second?
Yes. And that was the next thing I wanted to attach to that were units. So the units, since we're in feet and seconds, this is feet per second per second. We already saw that during that first 1 second interval. It lost 32 feet per second of velocity. So for every second that goes by, it loses 32 feet per second of velocity. I don't have a problem, although it doesn't really mean a whole lot, to write that as feet per second squared. I have no idea what a second squared is. It's just a quicker way of writing this. Ken?
What is the point of taking like the fourth and fifth derivatives then?
All right,
Taking,
well,
Taylor polynomial on the floor?
that's true. That's useful with Taylor and Maclaurin polynomials, which are really not part of this class, but become part of Math 241. He's talking about higher order derivatives, third derivative, fourth derivative, fifth derivative, very useful in those. There is such a thing that does have some merit here for the rate of change of acceleration. I don't know, can you think about what that would be like? You know, when you change your distance, kind of distance divided by time, that sounds like velocity. Velocity divided by time kind of sounds like acceleration. You change your velocity by accelerating or decelerating. What about if you change your acceleration? Anybody ever heard of that term? It's called the jerk. So a higher derivative here, although it's not used very often. I'm not calling you that, by the way. I'm not calling anybody that, but it is called the jerk. So the a prime of t, a lot of times you'll see it as the j of t, which is the jerk. So something, you're accelerating it, but you kind of do it abruptly. Think of that as like a jerk. Then that has a little bit of meaning, but it's not used very often. But the main use that you'll probably experience in this calculus sequence for higher order derivatives would probably be those things that you mentioned. In fact, that's how your calculator works, by the way, is Taylor and Maclaurin series. Your calculator doesn't know how to do a sine or doesn't know any of that stuff. It does all that stuff by Taylor and Maclaurin series, which are really good approximating techniques, very, very close to actual values. So we have the ability, knowing all these equations, we know the s of t, we know the v of t, and we know the a of t. We know their interrelationship. We took the derivative to get here. We took the derivative to get here. We will, later in this course, near the end of this course, we will reverse this process. We will start with acceleration, take the antiderivative to work our way back to velocity. And there are some inherent problems there that, constants may have been there and we don't know what they are, so we'll have to have additional information. But we will, part of this course, begin to reverse this process as well. Just so you know what type of thing you have here. And I think putting units along with it helps. So when we find the s of 2, what are we finding? The distance above the ground, or the height, or the position, right? All of those at time 2. So when we put that into the s function, I don't care numerically what it is now, but it's feet, right? It's a height. It's a distance above the ground. When you find the velocity at 2, we use the velocity function. And we get, again, a numerical value. I'm not concerned right now about that numerical value, but what are the units?
Feet per second.
Feet per second on this set of data. It could change on another problem. It might be meters per second or miles per hour. It could change. And then acceleration there isn't any place to put the 2, right, on this particular problem because it's a constant deceleration. Deceleration due to gravity. It's fixed. And that unit is feet per second per second. So we need to pay attention to the equation that we're using. What is it giving us? And the units that go along with that solution. So if you kind of pay attention to both ends of that, I don't think it leaves much room for error. I'm going to make up an equation. I'm going to put this in there. That was in the previous equation. When we took the derivative and then took the derivative again, didn't this term kind of help us decide that the acceleration was negative 32 feet per second per second?
Yes.
So this is the gravity term. Going to plug that term in. Now, we didn't have one of those in our first example. Anybody remember that's had any experience with these, what that term is going to be? Here's our gravity term.
Isn't it going to be like where you start? Like it's going to be when you take the derivative, it's just going to be 64.
Okay, so think about that. That's a good, I like that thought process, that when you take the derivative of this term, it's just going to be 64, right? So think about everything else
It's
being
like a
gone.
starting point?
Starting velocity. Okay, this is our kind of initial velocity term. It's going to. Now you say, well, that was gone in the previous one. It wasn't even there. Well, it wasn't there because what was the initial velocity?
0.
It was 0. That's why it was gone. There wasn't any t term, or you could say there was 0 t. Well, 0 was the initial velocity. And how about this constant that we tack on at the end, or we tacked it on actually at the beginning, right, of the previous problem? Starting position, initial position. So if I want it to start on the ground, what's going to occupy that position? 0. If you see a 0 there or there's nothing there, that means that it's actually on the ground at time 0. And you could validate that very quickly by putting in t equals 0, and you're going to get 0 for s. So when you see an equation like this, you kind of are thinking, there's the gravity term, there's the term that directly affects the initial velocity, there's the term that directly affects the initial position. So 64 feet per second, right, will be the initial velocity in this problem. So you can kind of pay attention to where things are, what terms are there, and so on. Notational thing to wrap up this section. The authors address this concept, which has already actually been addressed. The instantaneous rate of change is, in fact, the slope of the tangent, which is, in fact, the derivative. So these are all the same. So those terms can be used interchangeably. This is, I think, primarily just a notational thing. If you see this notation, delta y means the change in y. I don't know if you've used that notation in another math class before, but when you see the delta, it's a change in y over the change in x as the change in x is allowed to approach 0. This says exactly the same thing as this, because what is h? Wasn't h the change in x, right? We went from the first point to the second point by moving over h units. H was the change in x. So these two things really are saying the same thing. And there is another one here. Let's just validate that it, in fact, says the same thing. difference of the y values. Second, the f of x2 minus the f of x1, that's delta y. Same thing as this numerator. Difference of the x values, that's what h was. That's what delta x was. So these are all three, in essence, saying the same thing. Different ways of saying that instantaneous rate of change. I think that section 2.7, and I don't know that we'll finish this today, but I think you're not going to find a lot of really completely new information in 2.7. It's putting together everything we've done to this point in the book. So tell me if that's not the case as we go through it. There's something completely new. I'm thinking we've already had it, so let me know if, in fact, we have not. So they're addressing this thing that we've kind of partially addressed to this point called a derivative. It is the instantaneous rate of change. I think that's been said. It is the slope of the tangent line. So if we start with a function, we want the derivative, f prime. Did I talk about the prime, where that I think that might have come from? I think it possibly came from the word primitive, which was an early term used instead of derivative. That's my guess, is that that's why that's called f prime. It is the slope of the tangent. It is the first derivative. Now, we've actually taken the derivative of the derivative once. Didn't we just do that? Right? We started with s. We found the derivative. It was v. And then we found the derivative of v, and that was a. So wasn't a really a second derivative of s? We didn't call it that, but that acceleration function was really s double prime, or second derivative of s with respect to t. So the f prime is really the slope of the tangent, which is really the derivative, which is also the instantaneous rate of change. So that's why this 7th section in Chapter 2 really kind of just connects everything that we've had thus far. So, definition of derivative. This is the long way. We've already talked about this. Some of you know shortcuts. Those are wonderful. We're going to get to those. This is the long way. There are two ways that you can so-called use the definition of derivative. And I think we've had both of these. That ought to look familiar. That's the first derivative of the f function at a specific x value. Now, normally we'll just put an x there, and there'll be an x there, and there'll be an x there. But this, I think the emphasis here is that we know what x value we want to use. We want to use specifically the x value a. So that'll give us the value of the derivative at a specific x value. The other so-called this is the one that you'll probably use most often, but there is another one, and we have used it once. And that's valid. It is a definition of derivative. It does show starting with 2 points and letting the two x values get closer and closer together. That's exactly what we want to happen. So either one of these can be used. Once again, you'll probably use this one more often than the other one. All right, let's find the f prime of A for this function. Now, I'm hoping this is, based on what we've done thus far in Chapter 2, that this is an easy problem. Am I thinking right? So we want the f prime of A or the f prime of X. It doesn't really matter. It asked for the f prime of A, so let's go ahead and do the work for that. It's a limit. The stuff that occupies this place right here ought to be the slope of the secant, and then the limiting process takes this secant and makes it a tangent. So that's previous material in Chapter 2 to this point in time. So how does that numerator look? We want, according to this first, we want the f of A plus H minus the f of A, right? So the f of A plus H,
2A squared.
I think I'm going to run out of room in those brackets, would be 2, what, A plus H
Yes.
minus 9, A plus H plus 11. Does that work? From that, we're going to subtract what? The f of A.
2A squared minus 9A.
I don't have a problem if you don't like using the A's and you want to use X's. I don't have a problem with that. Then when you're done, everywhere there's an X, you'll put an A. That works. So let's square and double and do all that stuff. So we're going to have, what, 2A squared? The middle term would be 2AH. It gets doubled. 4AH. 2H squared. 9A. Subtract everything that follows. We should lose some terms at this point in time. What drops out? 2A squared minus itself. Minus 9A plus 9A.
11.
11 minus 11. That helps. Everything else should have an H. Let's factor that out. What do we have? 4A plus 2H minus 9. As long as H is not 0, that and that reduce to 1.
2H versus 0.
So we have, and you can combine these steps. I'm kind of trying to separate them, but that's fine if you want to combine them. There's what we have at this point. We still have yet to take the limit as H approaches 0, but as we do that, as H approaches 0, 2H approaches 0, and we're left with 4A minus 9. So what is the f prime of A? Apparently, based on what we have determined, it's 4A minus 9. What did we just find? The derivative, the slope of the tangent line, the instantaneous rate of change. It's all of those things. So if you know an A value from this curve, you can plug it in and it tells you the slope. So this is basically a little formula and that may not look right. We think, well, curves don't have slope. Yes, they do. They have variable slope. So as A changes, the slope changes. So at different places on this curve, we have different slopes. All you have to do is throw in the x value, multiply it by 4, subtract 9, and you have the slope at that point. That stuff we've already had, right? Different letters, maybe an A where there was an X, but I think we've had that process. Okay, let's go a step further with that. find the equation of the line tangent to this function. I hope it's the same function. It is. So we don't have to do that process again. At the point -122. So if we're eventually headed in this direction, we've got everything we need except what? Slope. We don't have the slope. We do have the point. Y minus the given y value equals slope. I'll leave that blank. X minus the given x value.
That -122.
Yes, -1, comma 22. I hope that's correct. Yes, that looks right. So we need the slope. Didn't we just do business on the other sheet there finding the slope of the tangent line to this curve?
Yeah.
So we know
-13.
f prime of A is in fact the slope, and what is A? -1?
Yeah.
A is our specific x value. In this case, it's -1. So what was the f prime?
4A minus
4A
9.
minus 9. Thank you. For -1s minus 9,
13. -13.
-13. Which goes right there. So y minus 22 equals -13, x plus 1. If that is the question on a test, you can stop at that point, because I know that you know what you're doing. So what do we really know about this function? We know a little bit. If the slope is -13, what's the curve doing in that general vicinity? It's decreasing, and in fact, it's decreasing pretty rapidly. To have a slope of -13, go down 13 units for every 1 unit it goes to the right. So it's headed downward at a pretty rapid rate. Here's one we don't really have all the ammunition we need, so we're going to have to come up with something. Three to the x. We haven't done anything like this yet. We've done polynomials, we've done rational functions, but we haven't done this. Let's suppose that we want to know the f prime of 0. Let's see how we can kind of use the same thought process to go about finding this. I'm going to go back to the definition of derivative. I'm not going to use the a. I'm going to use an x here because we've probably used it more than the other. Everybody in this room is going to be relieved when we get beyond the definition of derivative and we start to get some shortcuts. You will be, I will be. That's fine. We're still in this, and it does serve a purpose. What is this function evaluated at x plus h? Good. 3 to the x plus h
Minus 3x
minus 3 to the x.
over 8.
Is that all right with everybody?
Mm-hmm.
All right, we haven't done anything like this before. And in fact, normally at this stage, we expand t plus h squared or cubed or whatever, and we distribute all the coefficients. We can't do any of that here. So we might want to rewrite 3 to the x plus h.
X plus h.
Kind of a little reverse algebra here.
Log b.
3 to the x times 3 to the h. Is that true?
Mm-hmm.
Because normally you go the reverse of that, right? If you see the product of two things with like bases, you add the exponents.
Yes.
So if that's true in that direction, it ought to be true in the reverse direction. So 4, 3 to the x plus h. We're going to replace it with something that's equal to that. Do you think that's going to help?
Yes.
Why might that have a chance of helping? Because we have a common term now. We have a 3 to the x in this term and also a 3 to the x in this term. So let's factor out a 3 to the x. Is 3 to the x affected in any way by h going to 0? There's no h in it. So I'm going to move that out in front. All right, here we're blazing a new trail. Any suggestions, recommendations? What can we do to evaluate this guy right here? We don't have any little algebra trick that's going to work.
As 3 to the h goes to 0, it's eventually going to be 1, right?
Okay. I like the thought process. 3 to the 0
It's going to be 1.
is 1. 1 minus 1 would be 0, but h would also be 0, so we'd have 0 over 0. But that thought process is going to help us. Any suggestions? Are we supposed to let h be 0?
No.
We're supposed to let it approach 0. So let's do that. So let's say in this circled piece right here, let's say that h is that value. I don't know if that's enough. I don't know if that's close enough to 0, but it's on its way. So what is 3 to the 0.0001 minus 1 all over 0.0001? That's kind of what we're supposed to do, right? Is let h get smaller and smaller and smaller. Somebody run that through your calculator to see what you get. Anybody?
1.0986.
Anybody get same? Get some agreement on that? Do you think it's going to change much if we let h take on that value?
No.
I don't think it's going to change a whole heck of a lot. I think we've done pretty well with 1.0986. So if this is our, and it's an approximation, okay? We didn't use the smallest value we could possibly use for h because we tried that and we got 0 over 0, so that wasn't going to work. Did anybody run that through?
Yeah.
Pretty close?
Yeah.
Was it good enough all the way out to the 6?
Yeah.
Okay. So we've done real well with our first value of h. So I think that's a pretty trustworthy decimal value. Now we want the f prime of 0. Don't we put 0 in for x? Three to the 0 is 1, right? So the f prime of 0 on this problem is approximately, we feel pretty good about these decimal places, 1.0986. Anybody recognize that number?
Gravity.
No?
No.
It has something to do with 3.
I just did that.
Something to do with 3. The fact that we started with 3 to the x. Punch this on your calculator and see what you get. Natural log of 3. What's your calculator say that is? That is it. So we will see that later in this course, that when we get to this piece on the problem, 3 to the h minus 1 all over h as h approaches 0, that's the natural log of 3. If this had been 5 to the h minus 1, all over h as h approaches 0, that would be the natural log of 5. But right now, it's just this decimal, this ugly decimal. That's all we need from it right now. Okay, we're pretty close to being done. I think we'll stop there today. Wrap up 2.7 and talk about the test tomorrow. That'll be Thursday for us, and then the following day will actually be the test. Have a good afternoon.